Need no cheat. What we're doing today is starting chapter 6, exponential and logarithmic functions. So we're going to start this. We're going to start going over it this week, and then we'll finish it up after the break, after spring break. But the first thing we're looking at with these exponential and logarithmic functions is the parent function itself, or what a log or exponential function is. And we have two types. We have exponential growth and we have exponential decay. An exponential growth function, b to the x, where b is greater than 1, is considered an exponential growth function. So anytime the base, this b value is greater than 1, it's going to be considered a growth. And the reason we call it exponential growth is because, so 2 to the x would be exponential growth. The amount of change that happens in the output, the y value, as x changes, increases dramatically as we increase the value of x. Now, the first one, 2 to the 0, is just going to be 1. Now, if we look at 2 to the first, well, 2 to the first power is just 2. So we increase x by 1, the y value is increased by 1. Now, if we said x is now 2, so we're looking at 2 to the second power, well, 2 squared is 4. So we look at now 2 to the third. Well, 2 to the third is going to be 8. So the y value has increased by 1, 2, 4. We go to 4, it's going to be 16. 5 is going to be 32. 6 is going to be 64. And we keep increasing faster and faster. Now 2, for the most part, increases by a decent amount, but nothing dramatic. If we said y is equal to 10 to the x, our first few numbers would look similar. Because if we start off with 0, when x is 0, the y value is not going to be 10. It's going to be 1. Now we increase from 0 to 1, the y value is going to be 10. Guys, focus up here. When x is 2, it's going to go from 10 to 100. 3 would be 1,000. It's going to increase exponentially faster and faster. That's our exponential growth. Exponential decay, when the base at b value is between 0 and 1, it is going to be considered a decay function. So its growth at the base is greater than 1. It's exponential decay if it's between 0 and 1. So, first thing we're going to look at is determine whether it's exponential growth or exponential decay. So if we, and then evaluate for when x is 2. So y equals 2 to the x. Well, our base value in this case is 2. Is that greater than 1 or between 0 and 1? Greater than 1. So this would be exponential growth. Now the second part asks us to evaluate when x is 2. So we'd say y equals 2 to the second power. Well, 2 to the second power is 4. So 2 to the second power would be 2 to the x is growth. And when x is 2, we get a value of 4. Questions on A? Let's look at B. Y equals 1/2 to the x. Would this be exponential growth or exponential decay? Decay, because the base is between 0 and 1. Now we're going to evaluate this when x is 2. So we'd have 1/2 to the second power. Multiplying 1/2 by itself. Now we can do this in the calculator. We can say 1/2 to the second, which is 1/4. Questions on the first two? Let's look at the third one. Y equals 1.3 to the x. Would this be exponential growth or exponential decay? 1.3, is it greater than 1 or between 0 and 1? Greater than 1, so it has to be growth. Because if that base, the number that the x is being put to, is greater than 1, it's growth. If it's between 0 and 1, it's decay. Then the second part is to evaluate this when x is 2. So 1.3 to the second. And again, we can do this in the calculator, and it tells us it's 1.69. Questions on this so far? Y equals 1/3 to the x. This indeed would be decay because our base, that 1/3, is between 0 and 1. So it is decay. And then we want to evaluate this when x is 2. So we'd have 1/3 to the second power, which is 1/9. Questions on this so far? Questions on any of this so far? All right. This time we're just telling it whether it represents exponential growth or decay. So y equals 4 to the x. Would this be exponential growth or decay? Growth, because the base is greater than 1. Y equals 2/3 to the x. Decay, 2/3 is between 0 and 1. Number 3, f of x equals 0.25 to the x. Decay, because that base value is between 0 and 1. And lastly, number 4, 1.5 to the x. Growth, because 1.5 is indeed greater than 1. Questions on this so far? Now, the other type of exponential that we have is the natural base e. The expression, or e, is approximately 1 plus 1 over x to the x, so our exponential. So the natural base e is an irrational number. E is approximately 2.7182818286 is our e. Now with e, before we start talking about exponential growth and exponential decay, e is going to behave like most variables that we have, kind of like a little bit with pi, not so much, but like this here. E to the third times e to the sixth. E is a number, it's an irrational number. But if we multiply like bases, we do what? We add the exponents. So e to the third times e to the sixth is e to the ninth. Even though e does have a specific value, a lot of the properties of it will work the same as variables. So if we looked at the next one, 16e to the fifth divided by 4e to the fifth, well, 16 divided by 4 is 4. E to the fifth divided by e to the fourth, since we divide like bases, we subtract the exponents. 5 minus 4 is 1. Is it bigger on top or bottom? Top, so it's going to stay on top. So 16e to the fifth divided by 4e to the fourth is 4e over 1, or just 4e. Powers of powers. Multiply. So we're really multiplying 3e to the negative 4x by itself. So we could say that this is the same as this here. Well, our 3 times 3 is 9. E to the negative 4x times e to the negative 4x. We multiply something by itself, we add the exponents, which would be negative 4x plus negative 4x, which would be negative 8x. So 3e to the negative 4x squared would be 9e to the negative 8x. Square root of 16e to the 4x. Well, we can take this in two main parts. Because properties of radicals, we can actually change it to the product of the two parts. Square root of 16 is 4. Now, e to the 4x, we have to use some of the properties of radicals. We will get into this in the next chapter after this. But the nth root of a to the x is equal to a to the x over n. These are equivalent statements. A radical is the same as a fractional exponent. Or the denominator, the bottom of this exponent, is the index or root. And our power attached to our number inside the radical goes on top. So if we look at this here, e as a fractional exponent, the root, because it's a square root, so the number inside of it is 2. The exponent attached to it is 4x. We still have the 4, but 4x divided by 2 is 2x. So 16e to the 4x would simplify to 4e to the 2x. Questions on this here? Let's look at the next three. E to the 7 times e to the 4th would be e to the what? 24e to the 8th divided by 8e to the 5th. 24 divided by 8 is 3 over 1. E to the 8th over e to the 5th is going to be e to the 3rd. Since it's bigger on top, it's going to stay on top. Questions on this so far? 10e to the negative 3 to the 3rd. Now we can multiply it by itself 3 times, or we can apply this 3 to both terms, because we can apply it to both terms because there's not a addition sign in the middle. So really what we're saying is that we have 10 to the 3rd times e to the negative 3x times 3. Powers of powers multiply. And really with the 10, we're saying that we have 1 times 3. And this only really works if there's not a plus or minus between the terms. It's not 10 minus RE or 10 plus RE. We can apply it out this way. 10 to the 3rd, 10 times 10 times 10 is 1,000. Negative 3x times 3 is going to be negative 9x, 1,000 e to the negative 9x. Now, if we did it the way we did the one before, we could rewrite it as 10e to the negative 3x times 10e to the negative 3x times 10e to the negative 3x, because we are multiplying it by itself 3 times. Cubing. 10 times 10 is 100, times 10 is 1,000. E, multiplying like bases 3 times, so we're going to add all the exponents together. Negative 3x plus negative 3x is negative 6x, plus negative 3x is still negative 9x. So we still get to the same spot. It just takes a few more steps. The next one here, we want to take the cubed root of 64e to the 9x. So we're really looking at two parts. We're looking at the cubed root of 64 times the cubed root of e to the 9x. Cubed root of 64 is 4. Because we're looking for a number times itself 3 times. That gives us 64 is 4. Now with our e, we can do the exact same thing we did before. The number inside the radical goes on bottom. The power attached to our term inside goes on top. So we're really looking at 9x over 3. What is 9x divided by 3? And we still have our x. So 64e to the 9x, if we cubed root it, we get 4e to the 3x. And really this fractional root makes a whole lot of sense. And it makes introducing radicals a lot nicer. Questions on any of this here? Okay. Now, one of the last things we're going to talk about is the natural base function. This natural base e can also be considered growth or decay. Now, it's going to be an exponential growth when our exponent attached to e, this exponent attached to e is positive. Our positive exponent. It's going to be growth. If we have a negative exponent attached to that e, it's going to be decay. So if we look at this first one here, y equals 3e to the x. The exponent is what? Positive or negative? Positive, so we would actually say that this is growth. It doesn't matter so much about the number in front of it, it's that exponent. Is it positive or is it negative? If we look at b, the exponent is negative, so this would be decay. How about number 4, y equals 1/2 e to the x? It would be growth. 5, 4e to the negative x. Decay. And last one is growth. Not so much about the number 2x, but the fact that it's positive would make it growth. Questions on any of this here? We're good with this here. Yes? Okay.